Welcome to Web Handling. My name is Dave Roysum. In this video, we continue our instruction on how to calibrate nips, which is harder than calibrating dancers, which is in turn harder than calibrating load cells. Still, if you own a nip, particularly a winding nip, you must do these things, else you risk your product and process, and possibly even the safety of your operators. In earlier clips, we introduced the concepts needed to calibrate dancers. The fundamental concept was that friction is not only important, it may be as important or even more important than zero or gain, because it may be as large or even larger in size. This is a prerequisite for getting the most meaningful zero on your system. Then recall from the last clip that zero is not merely a calculation or calibration. It is a definition that varies depending on the specific machine component. In dancers, zero is the average of the just raise and just lower pressures. In nips, it is something entirely different. So, here is where we left off last time. We gave you the homework assignment to set up a control system for this very, very common winder arrangement. It applies to any winder with a layon, pack, or rider roll. In fact, it applies to many other nips as well, such as calendars, coders, printing presses, and many others. We got you started with best practices. For this particular diagram, we will fix the rod side cylinder pressure during run. It is this rod side where we will define our zero. The piston side will be where we do our control pressures, for say structuring the tightness of a winding roll. Let us be clear on one point. When we say fix side of the cylinder, we mean fixed during run. We may very well do something else during raise, lower, and lock. Okay, back to our assignment. How would you zero the rod pressure? Pause the tape and give me your best answer in as much detail as possible. Okay, time's up. What's your answer? Some people might say that the rod pressure should be just set at halfway between the just raise and just lower pressures, just as we did for dancers. However, that would not be right, because there are key differences. The first is that while dancers bounce up and down about a neutral point, the layon roll will continue to raise as the winding roll builds. Other people will say that the pressure should be set to the just raise pressure. The reasoning being that since friction opposes the general upward motion as the roll builds, we should counter that by working on the one side of the friction band. However, that would not be at all safe for the web or the winding roll, or perhaps even for the operator himself. If the operator sets zero or even low pressure, the layon roll may bounce off the roll. This could wreck the winding roll and possibly cause a safety issue. Thus, by convention, zero for this system is set to the just lower pressure. This is the lowest safe pressure. So, by convention and for safety, we set the zero as the just lower pressure. However, even this is not totally safe, as friction is not repeatable even in its unrepeatability. Thus, we may choose to add even more safety factor. While the zero that the operator never sees is set as described, the just lower pressure, we may not allow the operator to go to a zero on the zeroed system, or even very close to it. On larger machines, we may limit control panel settings to no lower than, say, 1 to 2 pli, 0.2 to 0.4 kilonewtons per meter, on that just lower zeroed system. Okay, now do you see how friction complicates our life? Well, just as with the dancer, we now conclude with two complications arising from the uncertainty in the real nip loads. No matter how perfectly we control cylinder pressure, the actual nip load on the winding roll will only be somewhere in that orange band. Good grief, as Charlie Brown says. Friction not only means uncertainty in actual real nip loading on our product, we also can't safely get to low nips. If we tried to get to a low nip, the layon roll may bounce off and possibly stay off long enough to wreck the winding roll and perhaps even causing a winder wreck. The result of the above setup procedure is the actual nip load versus control load on the cylinder. If we set zero control pressure as shown on the red dot, the actual nip load will vary somewhere from near zero to somewhat greater. Depending on the setup, we may not even allow to set that low of a nip load and may be limited to only settings above the dotted line. If we set a heavier load, as shown in green, the nip will vary from heavy to very heavy. In summary, friction ruins control precision and causes immense control confusion. In the figure below, we have a two-element system. First, we have a layon roller, much like the previous example. However, on this winder, we also have a core shaft system. This arrangement is common on 1,000 two-drum and other style winders. So, how would you set up, and particularly how would you zero the system? Pause the tape and write down your answer. Please answer in detail what you would do and why. So, how did you do? And what did you do? If you said that you would zero the layon roller as in the previous example, you would be absolutely right. And, as in the previous example, we will do all of our winding and roll structure work with the layon roll unless there is some other clear restriction that would prevent us from doing so. The new element here is the core shaft. First, we need to define a goal. With the layon roller, the goal was safety. With the shaft, it is entirely different. It is to minimize shaft bending. So, what happens if we don't get that right? If the shaft relief pressure is too low, the shaft will bend down due to the weight of the slides and overhung shaft. The nip will be higher on the ends and you will also risk wrinkling. On the other hand, if the shaft relief pressure is too high, the shaft will bend up due to excessive cylinder force. The nip will be lower on the ends, and you will risk wrinkling, but maybe not quite as severe as being too low. If you understand beam bending theory, it will be easy to determine what relief pressure to set for 0. Beam bending tells us that the shaft will not bend due to uniformly distributed loads, such as the core and the shaft weight shown in red arrows. However, it will bend big time due to bending moments applied on the ends of the shaft. So, to 0 bending, we need to set relief pressure to be the sums of the weight of the part of the shaft that is beyond the cores plus the weight of the slide assembly. The challenge is, however, checking your work. You can do the average of the just raise and just lower pressures to in effect weigh the slide assembly. Then you could weigh the shaft on a scale and portion out the lengths of the weight of the overhung portion. All of this is to make sure that the only loads on the core is its own distributed weight, shown in red arrows, which will not bend the shaft. Of course, we always check for system friction. If the friction is high, we may need to put up a little extra upload because friction opposes motion, which is in the building diameter of the winding roll. Of course, if friction is high enough, we may get wrinkles due to being too much and too little at the same time. Thus, again, we see the complications of friction. The best course is to reduce it at the design stage and check the result using the pressure difference method shown here. Okay, next and final challenge. Given a layon roller narrower than the winding roll and a core shaft, how would you set up this system? This system is common on many duplex winders. Okay, don't panic. I do not expect 99% of you to know this. First, you may need to do winding work using both systems in some cases. In any case, the goal will be minimize wrinkling as well as shaft deflection as much as it will be to get a not too tight nor not too loose winding roll using the nip. Second, no matter how well you set up this system, you can get wrinkling and web marking at the edges of the narrow layon roller if you have tender webs. Third, you can get wrinkling on the ends of the winding roll if the shaft bends too much, again on tender webs. To minimize shaft bending, you must use finite element analysis to balance the two nip load sources, as this problem is beyond simple hand calculations. Okay, let's summarize what we have learned in the last two clips. First, friction complicates everything. It causes uncertainty and actual real tensions on a dancer and actual real nips on a layon roller. This is true even if you control pressure perfectly. Friction also prevents us from running low tensions and low nips. Next, friction cannot be assumed to be negligible on any system with a pneumatic or hydraulic cylinder or a slide. I have seen many systems where friction loads were greater in size than the control loads. Also, friction must be measured, as the difference in cylinder pressures from the just raised to the just lower. Finally, zero must be defined, given a friction measurement and a goal that is particular to a particular element. Thank you so very much for watching this module in my Plant Practical series. Please stay tuned for the next clip where we will describe how to calculate and calibrate gain, which is in most cases, thankfully, simpler than zeroing NIP systems. See you then.